So I've got some demos that I want to show everybody with regard to pressure. More specifically, atmospheric pressure, right? We may not realize it, but around us every day, all day, well, most of us, I should say, there's air, right? And air is made up of gas molecules, right? We've got hydrogen, nitrogen, carbon dioxide, oxygen. There's all kinds of stuff in the air. And those molecules have mass, right? I mean, they just like the molecules that make up me as a person, this is a table, these handles, they have mass, right? And that mass is what's responsible for the air pressure we experience that we may not realize is happening. And the weight of all that gas is pushing down on us. And so air pressure changes as you go up in altitude because there's just not quite as much air pushing down on you as there is when you're down here where we are in Roseville, California. And so pushing down on us at any time under normal circumstances is about 15 pounds of force per square inch of surface area, right? And so this is what I like to tell everybody to do. If you make an OK sign, the area of that OK sign is about 1 square inch, right? And so in every OK sign, there's 15 pounds of force pushing on you. So if you go like this, that one little spot on your arm is 15 pounds pushing. 15 pounds, 15 more, 15 more, 15 more, 15 more, 15 more. And so the total amount of force pushing on you is pretty substantial when you add it all up. Now, why don't we feel it? Well, it's because of several circumstances, but most importantly, air is pushing on us from all directions, right? It's below us, it's down by my feet, it's above us, it's above my head, it's on either side of me. And so if I hold my hand out here, how come I don't feel force pushing from the air on my hand? Well, it's because that force is canceled out, right, by the same equivalent magnitude force in the opposite direction, right? So we don't feel it. And it's easy to move my hand around in the air because those two forces cancel out. So what happens if we have the ability to take away all the force from one side? Well, this is kind of how pressure works. If you have force pushing on one side from air pressure and force pushing on the other side from air pressure, you get zero net force. If you take away pressure on one side, now you have a net force in a specific direction. And so if all of a sudden there was no air pressure here, that force would push my hand that way because there is a substantial total amount of force there. And that's what this device helps us demonstrate. This is PASCO's atmospheric pressure demonstrator, and it is nothing more than a smooth piece of plastic, rubber, I should say, floppy rubber, with a handle on it. And the handle is aluminum. It's it's not magnetic. It doesn't stick to anything metal, right? There's no magnet there. But what we can do with this piece of rubber is we can put it down on flat surfaces just like that. And what we've done is we've taken the air that was just a second ago underneath it here and remove it. It pushes all the air out from underneath it. And now there's only air applying a force on the top of this. Okay, and what you'll see is, and students love this demo, it's impossible to pick this thing up off the table.
Don't believe
you. Right? I mean, the substantial amount of force pushing down from air pressure is holding it to this table. It's now I have to deal with the mass of this table, right? If the weight of this table is now part of what I'm pulling up here.
So what lifted the table?
So the force that I'm applying lifted the table plus the force of the air pushing from underneath, right? So, but just to show that it's not a trick, this isn't sticky, okay? There's no gooey stuff on here, right? And you'll hear a lot of people say there's no such thing as a force of suction, right? It's actually you're removing that force from the other side.
Nothing sucks in physics.
That's right. That's right. So, and so that force is pushing down, and it makes it impossible to lift this thing up. Now, if I put this on this stool here, okay, watch this. It comes up, no problem, right? So what's different? Well, you may not have noticed, but on my stool are small holes. And those holes actually allow that air pressure to push, right? And in fact, when I pull up on it, this piece of rubber air slides in underneath it, and that air pressure helps me push it up, pull this up off the chair. Okay? And so this is also a fun demo. These are what are called Magna Berg plates, right? And this is just a rubber O-ring. And what I have on top of this plate is a small access hole where I can connect a pump, basically. And so if I take this and I put this on top of that O-ring, it seats, right? But I can lift this thing up. And the reason is there's air underneath. There's air in that gap between this tabletop and the bottom of this plate. So it comes up no problem. But what happens if I remove that air? I remove that air pressure. So I'm going to hook this little pump up, and I'm just going to pump the air out. So I've taken the air out from between the bottom of this plate and the top of this table. And now you can't get it off the table, right? And I mean, and it's really on there. And so if I let the air back in, I heard a little hiss. You may not have heard it. It comes right off, right? So air pressure helps us everywhere. Now, I'm going to demonstrate in a little bit more dramatic fashion. Well, I think it's more dramatic. So this is a balloon, just a standard rubber balloon. And what I've done is I've put just a tiny bit of air in there, and I've tied a knot on the end. So I've trapped that air in there. No air can get in, no air can get out. But you'll notice that the balloon is real soft. It's not expanded. There's no tension in the surface of this balloon. That's because the pressure of the air inside, the force from that pressure is equal to that outside. So the air pressure inside is equal to the air pressure outside, right? It's easy to move the surface of this around. And just to show you that no air can get in or out, if I squeeze it, right, that air's trapped in there. So I'll put this balloon in this little chamber here, and basically what this is the demo that I just did with this on top of the table, but in a taller vessel, a taller airspace here. And so I'm going to take my pump, and I'm going to evacuate the air out of here. So what do we think is going to happen? So right now the air pressure inside the balloon is the same as the air pressure outside, right? So the balloon shape stays static. It doesn't change. So now, if we take the air pressure from outside around surrounding the balloon, there'll be no more force pushing onto the surface of the balloon. There will be only force pushing from within the balloon. And so let's see what happens. Did you guys see that? So what's happening to the balloon? The balloon is actually expanding. Without that force from outside, that atmospheric pressure from outside surrounding the balloon, pushing down, the force from inside is free to expand the surface of the balloon. And if we had a bigger chamber, that balloon would probably keep growing until that tension force from the surface stopped it from expanding. Or it popped, yeah. So if I let the air back in, what should we see? Well, now we're going to equilibrate the pressures inside and outside the balloon. Boom, and it goes right back to where it was. Still the same balloon, nothing different. So let's go one step further. Who likes marshmallows?
Who doesn't like marshmallows?
Okay. So, who knows how marshmallows are made? Actually, I'm kind of lying a little bit. I don't know exactly how they're made. But marshmallows are, it's a puffed sugar solution, right? So you have this sugary concoction that's like a slurry. It's real liquidy, but viscous. And then they foam it, they bubble it with air, right? And what happens is a bunch of air bubbles get trapped in there. And it makes these marshmallows nice and squishy. And so this is an air bubble. Now we've got trapped air bubbles in here. What do you guys think is going to happen when I put the marshmallow into the chamber? Okay, and so before I put our friend Marty the Marshmallow in there, I'm going to turn him around, And then I'm going to shut the lid. Oops. And now we're going to see what happens to our marshmallow as I remove that atmospheric air around it, leaving only the air trapped in the little bubbles that are inside the marshmallow. So what's going to happen? Well, we saw the balloon expand. Will the little bubbles in the marshmallow expand? Let's see. Marty's putting on some LBs.
Nice.
Okay. All right. And you might not be able to tell, but the marshmallow is actually starting to shrink a little bit. Okay. And Anne had a great suggestion earlier with the balloon. If we took enough air out of it and the tension wasn't strong enough, the balloon would eventually pop. So we can assume the same thing's happening here. Eventually, those little air bubbles in the marshmallow start to pop, right? And now I'm removing even more of that air out of there. Because as they pop, I'm now pumping that newly popped and released air out of there. And the marshmallow starts to shrink a little bit. So what's going to happen to the marshmallow when I let the air back in there? Okay? So, on the count of 3, 1,
2, and then 3.
1, 2, 3, go. All right, ready? 1, 2, 3, go. Oh. And so what I like to do is I like to tell students that this is actually a time machine, right? So they start small, they grow up, and then when you let the air back in, they get really old really quick. And that's what happened to Marty. Okay.